Okay, so good evening. After a long time, I have to wish good evening. So nice to see, I mean, some of you still there in my class. Okay, so if you look at the blackboard, what is happening here? I still haven't erased what happened in my last class. Okay, so if you recall, what we were trying to do, we were trying to prove that for complex eigenvalues, we are going to have a spiral. And I told you that it is going to result in a spiral shaped trajectory. What I did was to prove that your d theta dt is either strictly greater than 0 or strictly less than 0. Okay, it cannot be 0, right? So if it's strictly greater than 0, then I'm going to it is going to be increasing, and if it is strictly less than 0, it is going to be decreasing. Theta is going to be decreasing. Okay. So yesterday, if you recall, I reached up to this. Okay, and from here, I told you that because if the numerator is to become 0, so then the roots of the equation given by x by y, this, and like here you can see that this discriminant has to be positive, but on the other hand, since we are dealing with complex roots, the discriminant is already negative, right? So that is why I cannot get the numerator here as 0, right? And then I told you that Simon says straightforwardly commented that for c greater than 0, this is always going to be positive, but we didn't have any clue. But you will see that the clue is, in fact, very, very simple. Clue is very simple. Okay, and you are going to get it pretty fast. Okay, fine. See now, if you look at this, this expression is simply something like, say, I may call it maybe what should I call it? I'm trying to use some symbols. Say this is a P. This is a P, and then I okay. I'll after a while I'm going to do that. But before that, let me come to this part. So this part is nothing but if you see, this is simply tau square minus 4 delta, right? And this I can simply write as minus 1 into your 4 delta minus tau square, right? So obviously 4 delta minus tau square, that is strictly greater than 0 in this particular case, right? Okay, fine. So that is why if I write say maybe say q square, this is equal to say 4 delta by this, right? 4 delta by this. So then what I can do, this is going to be x by y is going to be something like d minus a plus minus I cube by 2c. Is it okay? Is it okay with everybody? Right?
Yes, sir. It's fine.
It's fine, right? So that means what I can do, I can write this root as something like your p plus minus I cube, isn't it? Where p, q are real. Is it okay? Fine?
Yes, sir.
Yes. So that and in fact yesterday I did one more mistake here. So this should have been minus. This should have been minus because I told you that this minus this, these two terms, if you take summation of those, that is going to be greater than, in fact, minus of this. Okay. So now you will see that in fact I don't even need that. Okay, so now let me concentrate on this. Alright. So this information tells you that I can simply say x by y squared. This is here already. I can simply write this as x minus the first root. So minus p, say minus I cube, say, right? And then x minus the second root, p plus I cube. Is it okay with everybody?
Yes, sir.
Isn't it? Right? I can easily factorize it like that. Okay? So this is simply going to give me C your x minus p whole square plus q square. This. Fine? Okay?
Yes, sir.
So then obviously this is positive, right? The whole thing is positive. So now we have already assumed that C is greater than 0. So this is definitely going to be positive. So I mean, depending upon whatever sign you choose for C, d theta dt is either going to be positive or negative. Is it okay? Fine. So that is why we are going to get a spiral out of complex eigenvalues. Okay. As I have told you yesterday, like say if the imaginary part is 0, so then spiral is going to reduce to a closed circuit. Okay. You have already seen that. Fine. So now let me tell you what I'll summarize all the different types of critical points. Before that, let me just tell you how a spiral is going to look like. Okay, so now as before, depending on whether the real part of the complex number is positive or negative, right? The spiral is going to be stable or unstable. Okay, if the real part of the complex eigenvalue is positive, the spiral is going to be unstable, and if it is negative, it is going to be stable. Okay, so then let me just try to do one example so it will be clear to you. So let us take this a equal to 318 and 2 minus 9. 2 minus 9. Okay, and yeah, and the initial point is x0 equal to 1, 0. Initial point is x0 equal to 1, 0. So we'll try to do it quick. So here your lambda is going to be given by what? Lambda is going to be given by what? Tau. Tau is, this is minus 6 plus minus, then again minus 6 whole square minus 4 delta. Delta is minus 27 minus 36. Am I fine? Okay. 27 minus 36. I think that is going to be 63 minus 63. So this divided by 2. So minus 6. This is 36. This is 252, right? 252. And this is going to give you what? 36 minus 2. Yes. minus 216, right?
So this will be plus 252.
It is plus. Am I taking some other example? Oh no, it is, yeah, it is, because I want this to be a complex. So this is minus 18. I made a mistake there. So that means this is going to be plus. This is going to be plus. So yeah, fine. So 216, can you, some square root is going to come? Did I do some mistake? Minus 93, that is minus 6, 36. So no, this is going to be different now. Huh? Sorry, this is going to be different. So this is going to be what? Minus 27 plus 36, right? Yes.
It will be
So
9,
it will
sir.
be 9. Huh?
9.
It is 9. No, but 9, that is going to, yeah. But then I'm going to end up with 0. What mistake I'm doing? Did I do mistake here?
So
No.
was
Sorry.
It was
No.
plus
They
18.
are. These cases for equal roots. I don't want to do that. In fact, I was looking for a complex root. No, this is going to give you. This is going to give you equal root. This is going to give you equal root. So it is simply your minus 3. It is simply minus 3. Okay. So, okay, let us work it out, and I'll just tell you how this file is going to look like. Okay, so minus 3. So then a plus 3i. This is going to be, this is 0, right? No. This is 6 minus 18 to minus 9 plus 3 minus 6. Yeah, fine. So it is basically 1 minus 3, 0, 0, right? So you are going to have 3, 1 as your eigenvector. 3, 1 as your eigenvector. Okay. And again, here you can see that this is negative. This is negative. So 3, 1. So 1, 2, 3. So 1. So okay. So obviously, because the eigenvalue is negative, right? So this k1 is going to look like this. Now you know that. And then what is going to happen? Like if I start with 1, 0, if I start with 1, 0 here. So anyway, like I have drawn it like this, right? Just to get the I mean how the straight line looks like. So I can make this as 1, 0 now. Okay, right? So the going to evolve like that. Okay. So here it is going to be something like this. If you try to find out the trajectory originating at the point 1, 0, it has to be it has to be something like this, isn't it? It has to be something like this. Is it okay?
Yes, sir.
Because this is degenerate unstable node. Degenerate stable node. Okay, fine. So now, like say, because we were in complex eigenvalue, so in complex eigenvalue, what is going to happen? As I think I told you yesterday. So the it is going to be like this. Okay, so if your eigenvalue is alpha, plus minus I beta, then if your alpha is positive, so then this is going to be spiraling out. And if it is negative, it is going to spiral in towards the critical point 0, 0. Okay, so this critical point 0, 0, it is called a spiral point. No? It is called a spiral point. In fact, I don't like this nomenclature. It is called a spiral point. So it is going to be called a stable spiral or unstable spiral, depending on this. Okay, and it is also called a focus. It is also called a focus. Okay, so we have covered everything. Now let us try to summarize it. You will see that the summarization is very interesting. How it is summarized. Okay. Okay, so what I'm going to do, like say, this is summary of critical points for it is linear systems. Linear system. Okay, fine. Just wait for it to. Okay. So here, I'm not going to show you the XY plan. Okay. Rather, what I'm going to do, I'm going to show you your tau delta plan. Tau delta plan. Although, eventually the critical points that I'm going to, draw, they will be shown in XY plan. But here, what I'm considering, I'm simply considering tau delta plan. Is it okay? Fine. So then, what is important here is the discriminant, isn't it? So depending upon the discriminant, that was tau square minus 4 delta. Right? Is it okay? Fine. And from here, if this is equal to 0, you get delta to be equal to 1 by 4 tau square. Right? This is fine?
Yes, sir.
Right? So in the tau delta plane, this equation, if delta is a function of tau, it is going to be what? A parabola. Isn't it?
Yes.
It is going to be a parabola. So suppose this is the parabola. Suppose this is the parabola. This your tau square equal to 4 delta. Suppose this is the parabola, tau square equal to 4 delta. Okay. So then what is going to happen? Inside this parabola, here, inside this, what is going to happen? Your tau square minus 4 delta, it is going to be less than 0. And outside this, your tau square minus 4 delta, it is going to be greater than 0. Is it okay? Fine?
Yes, sir.
Fine? So then, what is going to happen? Like again, in this portion, what your tau is greater than 0. Isn't it? In this portion, tau is greater than 0. And in this portion, tau is less than 0. Okay. So this portion corresponds to what? Your unstable critical points. Well, irrespective of this graph, irrespective of this parabola, your the right hand side of this delta axis, it is always going to be positive tau, and left hand side is going to be negative tau. Is it okay?
Yes, sir.
Yes, sir.
Fine. So now let us see what is happening. So here we are going to get, in this portion we are going to get, unstable spiral. So it is going to be something like that. And here in this portion we are going to get stable spiral. It is going to move towards stable spiral. Okay, and when just a minute. It becomes pure imaginary when just a minute. See, your lambda was what? Tau plus minus this one, tau square minus, right? Okay, so it is going to become pure imaginary when tau is equal to 0. Is it okay? Isn't it? Fine. Whatever imaginary part will come, it will come only from this portion, isn't it? This, if tau is equal to 0, right? What we are going to get? So that means along this delta line, I am going to get this. I am going to get center, isn't it? I am going to get center. Is it okay? Fine.
Yes, sir.
Yes. So now, when this is tau square minus 4, this is greater than 0. This portion. So I am going to have, real roots, isn't it? I am going to have real roots. Okay. And then again, when tau is positive, I am going to get positive real roots, right? So in that case, what I am going to get here, I am going to get what? Nodes, right? I am going to get something like this. I am going to get something like this. If this is my this one and this one, something like, am I okay or? Yeah, fine. So it is going to be spiraling out. It is going to be spiraling out. So I am going to have unstable node here, and similarly here I am going to get stable node. Okay, fine. And when tau square equal to 4 delta, then I am going to have equal roots, isn't it? I am going to have real roots which are equal. So for equal roots, what we get? We get degenerate. Here it is going to be unstable node, and here it is going to be degenerate stable node. Is it okay? Fine. And then again, what was happening? Like, if you recall, my equation was this. From where I was trying to find out the value of lambda. So then what is going to happen? If lambda is delta. This is delta. If delta is negative, definitely I am going to have distinct real roots having opposite signs, isn't it? So along this line where delta is negative, what I am going to get? I am going to get something like what?
Shadow.
Saddle. I am going to get something like saddle. So one is going to be this, one is going to be this, and all the other trajectories, they will be moving away from origin towards the dominant eigenvector. And I want to tell you that in my yesterday's class, when I was solving one particular, particular system, so where I got a saddle, these three were okay, but this line somehow, instead of starting from here, I drew it from here and I gave the orientation like this. This was wrong. Please correct it. Okay, you should always remember that everything will be moving towards the dominant eigenvector. Always remember that. And dominant eigenvector will be given by the larger of the two eigenvalues, whether it is positive or negative. Is it okay? So here, because one eigenvalue is always positive, obviously the positive one will be larger. Okay, and it is going to be moved towards that, and you know that being positive, it is going to be unstable. So in this particular case, here I get a 7. See, if you can recall this diagram, then critical points. It is just what should I do? What should I tell? It is just very easy. Okay, fine. So I think this is about linear system. So now I want to move to plane autonomous system, which is non-linear. Okay. So now I am going to talk about linearization and local stability. So this, have you understood it completely? The summary part. Is it okay?
Yes, sir.
Yes. Right? Okay. So you please go through it once again at home, like in the Jiten books as well as in Simon's book. It is explained there. But I think in the Jiten it has been explained in a much lucid way. Okay. So this linearization is very, very interesting. This linearization concept, I will tell you how it has come about. So next thing that we are going to do is this is whether you write Z or S, it doesn't matter. Linearization and local stability. Okay. In fact, I had already told you about stable, unstable earlier. I'll just show you a beautiful example. I am going to show you a beautiful example. But before that, why the concept of linearization? See, earlier what we did, like in linear system, we were still considering your autonomous system like this, right? But what we did for these two functions, we had chosen some linear expressions in x and y. Right? Okay. So now, once we move from this linear, this was linear. Once we move from linear to non-linear, the very first thing that is going to happen is, so for the linear equation, 0, 0 was the only critical point we had chosen. Is it okay with everybody? 0, 0 was the origin. The origin was our only critical point. This was the only critical point. This was the only critical point. Okay. Fine. And basically, it could have been something else also, x naught, y naught. But what happened? We used some transformation so that x naught, y naught can be converted to 0, 0. So basically, we ended up with only one single critical point. That is the most important thing here. Okay. But when you are going to consider nonlinear system, where f of xy and g of xy, they are going to be nonlinear in x and y. So then you are definitely, I shouldn't say definitely, you are likely to end up with more than one critical point. Is it okay? Isn't it? For example, in the logistic growth, we ended up with two critical points, y equal to 0 and y equal to k. Right? That was a one-dimensional system, isn't it? Fine. Is it okay with everybody? Because if you recall, my system was something like this: r y 1 minus y by t, something like this, right? My this one f of y was something like this. Okay, so this was non-linear. So it resulted me in more than one critical point. So here also, the striking difference between linear and non-linear, the very first one is you may end up with more than one critical point. Okay, fine. So now, what I'm going to do, linearization, I will come back in a little while from now. But before that, let me introduce you to a very, famous and familiar problem they consider in order to understand, stable and unstable concept, which I have already done. But here, what I'm going to do, this problem is called sliding bead problem. Sliding bead problem. Are you already aware of this sliding bead problem? Yes, anybody? Yeah? Is anybody aware of this problem? Looks like the answer is no. Okay, fine. So what we are going to do here, we are going to consider in the xj term, don't worry about it. They are just avoiding that variable y, because y later on we are going to use for plan autonomous system. Okay, say suppose I have a curve like this. Suppose I have a curve like this. Is it okay? This curve is j equal to gx. J equal to gx. Okay, and suppose this is kind of a metal wire. This curve, suppose you may consider it to be in the shape of a metal wire. Okay, then you consider a very small bead, very small bead. Bead, you know, right? Those necklaces, those garnets, right? It is some beads are tied with this, and many people wear that, right? This is bead motif kind of. So then here, suppose this is x1, and suppose this point is x2, this point is x3. Can you tell me what is the significance of x1, x2, and x3? Yes? Yes?
The local
So X1 and X3 as the local minimum.
And X2 is local maximum. Okay. So then what happens? The motion of this bead, it can be like this g of x prime. So it can be mathematically modeled with a function like this. Okay, x double prime equal to g of x comma x prime. Okay, so now I mean if I introduce the variable, say your x prime equal to y, if I introduce the variable x prime equal to y, so then this is going to reduce to y prime equal to g of xy, right? Isn't it? So that means I have a plane autonomous system given by and y prime equal to g of xy. See, this y is nothing but something like this is also a function in x and y, isn't it? Right? It is something like f of xy now, although the value is simply y. Okay? So this describes a plane autonomous system. This describes a plane autonomous system. Is it okay with everybody? Is it okay with everybody?
Yes, sir.
Right? So now what is going to happen? If you place these and these 3 points and these 3 points, 3 points, so you know that they are going to remain stationary there, isn't it? If you place it there, they're not going to move from that until and unless you apply some force, whatever it is, right? But if you place it there, they are simply going to have zero velocity, isn't it? Right? So basically x1, x2, x3 are 3 critical points for this system. Is it okay? Fine. So now suppose I consider this critical point x1. So now if you release a particle nearby this point x1, say somewhere from here. So depending upon with what velocity you are releasing this bead, what is going to happen? Like say if you release it with a very like say small velocity, then probably what is going to happen? It is going to go towards this up to this point, again going to come back, and after a while again it is going to come back to this point x1, right? Up to this, is it fine?
Yes, sir.
Yes,
Isn't
sir.
it? Now, if the velocity is more, then it may so happen that it is going to go over this hump. Hump, you know that camel hump, right? This is simply that it is simply like the camel hump, isn't it? Right? So it is going to go over this hump and it may reach nearby this critical point, isn't it? Right? So basically, are you getting my point?
Yes, sir.
Right? It may not go there, or I mean, it may come back, right? But there is a possibility that with high velocity, it is going to go over this, right? And again, you know that even with smaller velocity, if you release something from here, it is not going to come back to that point, right? So through this example also, you can understand the concept of, stable and unstable equilibrium points, right? So obviously, these 2 points where I have a local minimum, they are going to have stable critical points, whereas the local maximum point, it is going to be an unstable critical point. Is it okay? Fine. So now let
Sir,
me.
why this 3 points is calling critical points? What is the logic?
What is the logic? So if you place the bead there, right? It is going to remain stationary there.
Okay.
Right? If you consider them to be the initial point itself, it is going to stay there. That's it. Okay? Fine? Now, Okay. So now let me give you the definition of stable, critically stable, and unstable critical points. And for that, although eventually for all practical purposes we are going to use planned autonomous system, but the vector that I'm going to display here, you may consider that to be a vector in Rn also. Okay. So only thing is that in that case, the distance between 2 points in Rn. So you are going to use that. The Euclidean formula. Okay, Euclidean distance formula. Is it okay? Fine. So now let me come to stable critical points. Okay. So let us consider an autonomous system. This may be involved Gx. Okay. So I don't know whether G x bar is linear or non-linear. So obviously here now we are characterization enough to consider it to be non-linear. Okay. And suppose the next information is x1. This is a critical point of this system. Okay. Next, let us assume that I have another point, x naught, which is not equal to this critical point. Okay. Fine. These three, whatever I have written, this is clear to you. Okay. And also, let us assume that this point x naught bar, it satisfies the initial condition this. Initial condition this. Okay. So then I am going to say that your x1, this is a stable critical point if for any given radius rho greater than 0, we can find r greater than 0, your such that your this here, I think this is good enough. xt minus your x1, it is just a minute. It will just a minute. It is going to start here in just a minute. Okay, this is fine. This is I'm just trying to do it in a different way. Trying to do it in a different way. This is less than rho, provided, let me write it like this. Provided, I'll explain it to you graphically. Provided your this x naught minus x1 or x1 minus x naught less than r. You just have a look at this. Okay. Basically, I'll tell you what is happening here. Maybe if I explain it graphically, it will be clear to you. Say, suppose this is a critical point, say x1. Okay. Now I have an initial point. X naught. Okay. Now I have chosen the initial point x naught in such a way that it always lies, I mean, say the distance between these two is less than this, less than r. Okay, so now obviously, because x naught is not a critical point, it is going to move away from this, right? It is going to move away from this. So it may so happen that, okay, its trajectory is going to be something like this. Okay, right? So if it is such that it always remains inside a circle of radius r centered at x1, then I say that your x1 is a stable critical point. Is it okay with everybody? Do you want me to elaborate it more?
Yes, sir.
Yes, sir. Please elaborate.
Okay, just a minute. Maybe I maybe I let me make that closer. Because that R concept I still haven't. Okay, see, this is x1. So let me see now what I am going to do. Simply forget about this x naught. Huh? Let me draw a circle of radius r centered at x1. That is what I am doing. Okay, fine. Let me even not worry about it. So this is I am drawing a. Okay, so this is a circle of radius r. Okay, so what I am doing, this r is very small. What I am doing, I am choosing my initial point to be very close to x1. This is fine, right? I choose the initial point to always lie inside the circle of radius r centered at x0. Is it okay? Sorry, x1. Is it okay?
Yes, sir.
Fine. Now it is fine, right? So then what happens if now say obviously x0 not being a critical point, it is going to move away, right? It is going to move away from it. So now if its trajectory, whatever it is, see, I can consider its trajectory to be something like this, a closed circuit, right? Or I can consider its trajectory to be something like this also. Something like this also, right? Something like this also. Is it okay? I have a pink one, and I have a blue one, right? But if the trajectory is such that, I mean, it is always going to lie inside a big circle of radius rho centered at the same critical point x1, then we say that x1 is a stable critical point. Is it clear now?
Sir, but why? The definition is like that.
Why the definition is like that? Okay, fine. See, basically, the definition is like that. It is telling you that eventually, final point. Say, suppose the last point is say suppose x final. Huh? Last point in the trajectory is x final. Okay, or okay, fine. Not necessarily the last point. All the points in the trajectory, they are going to lie nearby the original critical point. That is the case. So maybe once I explain to you the unstable critical point criteria, so then I think it will be more clear to you. More clear to you. Okay. See, what is the definition of unstable critical point? I'll come back to the asymptotic critical point later on. Sorry, asymptotically stable critical point later on. But
Sir,
yeah,
sir,
yes,
may I add one point here? Hello.
yeah, I'm listening. Yeah, tell me.
Okay, so it is like, sir, in case of 2D, suppose you are assuming 0, 0. I mean, for example, you are assuming 0, 0 is the critical point. That means what is happening? All the trajectories actually come towards the critical point. That means if you take that means all other trajectories actually, I mean, come closer and closer. If we something like, if you think about the definition of limit or something like that, then what is happening? That distance between the 2 points, I mean, is very, I mean, close. I mean, as it's arbitrarily small, basically. So that we can relate from in 2D case to, I mean, from the, I mean, planar case to here in whatever
No,
you are
no, that
discussing,
is
basically.
fine. Even here, I can visualize it as a 2D case only, right? I'm not considering it a sphere or something like that. I'm still saying that it is a circle. Okay. See, basically what happens, like obviously, it is not necessary that like say initially whatever distance the initial point was maintaining, the trajectory is going to be such that it is going, the distance between the critical point and all the points on the trajectory is going to be less than whatever was there at the very beginning. It is not necessarily so. It may go away from that. But the thing is that it shouldn't go too much away. It is always going to remain within a certain limit. Is it okay now? So let me now just let me do the unstable critical point. I think then it is going to be more clear. Okay. See, what is unstable critical point? Let me tell you. Okay. See, I have a bigger circle here. I have a bigger circle here centered at rho. Okay, fine. Say, sorry, of radius rho centered at x1. Okay, so what I do, I take an initial point which is very close to x1. This is x0, and I have taken it in such a way that, I mean, it lies inside a very small circle of radius r, centered at x1. Okay, so now what may so happen that once my trajectory starts, it may come back inside this circle of radius rho, but it may so happen that at least for some time, it may go outside this circle. Okay, so basically, if I have this, for at least for some 1 t greater than 0, right? Then I say that this point x1 is an unstable critical point. Now, is it clear to you? Now, have you been able to differentiate between the stable and unstable part? Right? Was it Tanmoy who asked me the question? Why stable is defined in that way?
Yes, sir, but it is not fully clear to me.
Basically, what happens, the trajectory is not going to move far away from that critical point. That is the thing. That is the thing. I am trying to limit it within a distance rho from the critical point. That's it.
Yes, sir. Sir,
yeah.
For some neighborhood of this dependent variable, if we get some neighborhood of the independent variable, which is very close to the critical point, so I am confusing in this two terms.
No. You don't worry about the independent variable. No. You don't worry about something like whatever you did earlier, like like that continuity, those kind of things. No, no, don't try to rope that in. You are going to be more confused. You just try to think about it physically. Okay, you just try to think about it physically. Okay, I'll give you an example. And again, see, this row I have told you, row greater than 0, right? I haven't quantified it. Isn't it? I have not quantified row. How big row should be? Isn't it?
Yes.
Right? I haven't quantified row. Right? So basically, if you know that it is eventually going to move away from the critical point, the trajectory is going to move away from the critical point, then it is unstable. That's it. And again, what is asymptotically stable? What is asymptotically stable? Apart from being stable, So stable means simply it is going to be like the whole trajectory is going to lie nearby this critical point, right? Okay, but it may so happen that limit t tends to infinity, this is x1. If it comes back to the critical points, then we say that this critical point is an asymptotically stable critical point. Have you understood now?
Yes.
Asymptotically stable critical points. Okay, so that means, see, I have a situation like this. See, this was your original circle. This was your original circle. This is R. This is x1. This is say x naught. This is say x naught. It may so happen something like after a while, it is going to come back like this. Okay, right? It is not necessary that I mean, it may leave this circle. It may leave this smaller circle here. But again, it is coming back. Okay, so now, can you tell me whether a center is asymptotically stable or not?
I think no.
Not you think, it is no.
Yes. Because we could not get a
It
trajectory.
is not coming back to, it is hovering around the critical point, right? It is
Yes.
not coming back to the critical point. Is it okay? Fine? Now is it clear? And see, it is basically, it is about this quantification of this row. How big row you are allowing in order to achieve stability. So basically, we want it to be close enough to the critical point. That's it. We want all the points in the trajectory to be close enough to the critical point. I just don't want it to move away. That's it. And again, always remember, stable is coming back, unstable is going away. Okay, stable is coming back, unstable is going away. That's what it is. Okay, fine. So now let me.
Sir.
Yeah.
Sir.
Yeah.
So it is basically while defining or stating this stable critical point and unstable critical point, we have three things, right? One is x1, one is initial point, another is x of t, right?
Yeah, x of t is nothing but the location of the
that is can we think like that, that as x1 is very close to x naught, what is happening to the neighborhood neighboring trajectories basically? Because from the both the definition we can see that at if you consider x1 to be a critical point, that means the behavior of the critical point as close to the initial point, behavior is the behavior of the other trajectories actually.
No, exactly what we are doing. We are trying to find the trajectories starting at some points which are very near to the critical point. Okay, and we don't want those trajectories to move away from the critical point. That's it. But here the question is like, how much? Yeah. You see, I know what basic question. I mean, what is going around Thomas' mind. See, I can give you an example. So suppose I am considering a center. I am considering the critical point as a center. Okay. Now, one thing is, oh, okay, you are never going to get that. Yes, yes. You may think that I made it a center like this, right? Which is hovering around the critical point, but its radius is bigger than this row, right? Am I still going to get that? Am I still going to get this center as a stable point? It is no, because the initial point has to be nearby this here. Because in case of center, what is going to happen? Because this is very nearby this chosen critical point, so it is going to hover around this, something like this. It should be something like this. It has to be inside this row. But again, the quantification of that row, it is kind of, I mean, not very clear. Okay, fine. So what I suggest is that there are two examples. There are two examples in Coulin's book. You please have a look at that. They are pretty straightforward. They are pretty straightforward. They are talking about stable and unstable equilibrium point and asymptotically stable critical point. They are giving a couple of examples. And for the unstable part, what they have done, they have simply taken the example of that logistic growth that I had taken. Logistic growth I had taken. So now I'll just give you some idea about linearization. After that, I mean, probably in my next class, I'm going to do it for a train autonomous system. So now, what is linearization? Okay, what is linearization? See, I mean, suppose I am considering a function of one variable. Say, I am considering a function of one variable. That y is my dependent variable, x is the independent variable. And suppose I am considering the graph of the function. Okay. Maybe. Okay, fine. So then suppose I'm considering this point. I'm considering this point, and I'm drawing a tangent to this. Okay. So now let me call this point maybe x1, because now for critical point I'm going to use x1 comma y1, something like that. Okay. So suppose this is the point x1, right? So now, suppose I am considering a neighboring point here. I am considering a neighboring point here. Okay. And suppose this point is simply like this much is say delta x. Okay. And earlier, what was happening? So this is y. Suppose this is y. 1, this is y1. So this point is x1 y1. So basically x1 y1. Okay, and then like say this is delta y. This is delta y, right? So now I know the value of y at the point x1. This is equal to y. I already know it, right? Suppose I am seeking the value of this y at a neighboring point, right? So then you know that the actual value is here. The actual value is here, isn't it? Fine. So at this point, this is nothing but y x1 plus delta y. Is it okay with everybody? Fine.
Yes, sir.
Right? But if instead of choosing this value, I choose the value corresponding to the point that lies on the tangent, right? So then, if you look at this point, then what I'm going to get, like, suppose this distance I call it dy. This distance I call it dy. So basically, what I am getting, I am getting the value of a function which corresponds to a point lying on the tangent plane. Is it okay? Are you getting my point?
Yes, sir.
Yes.
Yes,
So what will be that value then? What will be that value?
y1 plus dy.
Y1 plus dy, right? So y1 plus dy. So in fact, this tells you the difference between your delta y and this total differential dy. But the thing is that, so this y1 plus dy, what is going to happen? The equation of this straight line, this is y1 minus dy minus y1. So this is equal to your y prime x1 into x minus x1, isn't it? Yes? Are you getting my point?
yes, sir.
Yes, sir.
Right? So basically, this is the linearization. So what we have done, instead of the value of this, I am approximating this with a value, simply your y at x1 plus that dy. Okay, because here, see, this is going to give me this x minus x1. Yeah, so that is delta x. That I can I write it as delta x? Yes, right. So that x, this x, I can replace it with your what? X1 plus delta x, isn't it? So basically, what I get here, I get your dy equal to this. So this is nothing but total differential. So what is being done here? So I am simply replacing it with y prime x minus x1, isn't it? Right? Fine. Okay. So this concept is called linearization. Okay. So are you getting my point or not?
Yes, sir.
Yes. Why it is called linearization? Because you can see that here again this y prime at x1. This is going to give you some fixed value. This is going to give you some fixed value, say C2, right? This is C1. This is also some fixed value. So C1 plus C2, x minus x1. That is a linear function in x. Is it okay? Fine. Right?
Yes,
So
sir.
that is why, yes. That is why this concept is called linearization. Now, the thing is whether linearization is a good idea or not. See, in the neighborhood of this point, it is a good idea. But once you move away from that, it is not a very good idea. Okay, but fortunately for us, we are going to use this in case of critical points, right? So we are going to check whether a critical point is stable or unstable by what? Checking some points very close to it, which are going to be initial point, isn't it? So that is why we are okay here. We are okay here. But again, remember, this linearization, most of the time it is going to give you very good result, but in certain cases it may not. As your initial point moves far away from the critical point, it may not give you better approximation. That is what it is. But linearization is still, it is almost giving you perfect result. Okay, so
Sir,
yeah.
so can we do Taylor series expansion and truncate the third term onwards? So in that way also we can do
No,
linearization,
it's
right?
the same thing. I mean, like say Taylor series expansion. I mean, if you truncate it after the first derivative, it is nothing but linearization, right? Because the second derivative onwards, you are going to have non-linear term. You are going to have x minus x1 squared term, isn't it? Right? You are going
Yes,
to
sir.
have something
Yes.
like this. Something like
Yes.
this. That is going to make it non-linear. So it is the same thing. Although they call it Taylor series, but I would like to call it the tangent line approach more. Okay. So now I'll come to a very good example and then I'll finish this class.
Sir, can you do linearization of every function?
Yes.
But the mean value theorem maybe fails somewhere.
No. Every function means there has to be some continuity and differentiability criteria there. Okay. So that is why we always do it in the neighborhood of some points. Okay. So if I assume that the function is differentiable at a point, so that is going to, guarantee you some kind of, smoothness of the function in the neighborhood of that point. Okay. I'll come to that in my next class probably. Okay. So now let us simply consider. Your this example. Say, suppose dx dt. This is equal to simply g of x. Okay, fine. And suppose suppose x1 is a critical point. X1 is a critical point for this system. Okay, although it is one dimensional, but still this is going to illustrate a lot of things. So then I can linearize this with the tangent line approach as we just did earlier, right? So then this is approximately going to be equal to g at x1, right? Plus your g prime x1, x minus x1. Is it okay with everybody? Fine?
Yes.
Is it okay?
Yes, sir.
Right?
Yes, sir.
So now let me call it so fine. So can you tell me what is the value of g of x1? X1 is a critical point.
Zero.
0. Because how do I find critical point? By plugging in the right hand side to be equal to 0, right? So if x1 is a critical point, g of x1 is going to be 0. Is it clear to everybody?
Yes, sir.
Right? So this is equal to your simply g prime x1, x minus x1, and let g prime x1, let this is the lambda 1. X minus x1. Okay, so then you know that I can always solve this one, isn't it? Like say it is going to be what dx x minus x1 equal to lambda 1 dt, right? So this implies your ln x minus x1. This is equal to. Should I bring ln here? Okay, fine. Don't worry. Maybe I can write it directly there. But anyway, fine. So eventually, I am going to get your x equal to x1 plus your c e to the power lambda 1, something like this. Yeah, this is good enough for me. This is good enough for me. Okay, is it okay?
Yes,
Fine?
sir.
Fine. So now, see, this is going to give me the solution for x. Although this is a scalar equation, this is a scalar equation. So that you may consider this to be a part of some system, like say one variable was x, the other variable was y. Still, I mean, it is going to give you some idea, right? Now, like say, as t tends to infinity, like whether x1 is going to be a stable or unstable critical point, it is going to be determined by what?
Lambda 1 is positive or negative.
Exactly, whether lambda 1 is positive or negative. Okay, so that means if lambda 1 is negative, your x1 is going to be a stable critical point, isn't it? Right? See, this is in fact xt equal to this, isn't it? So if lambda 1 is less than 0, what is going to happen? Limit t tends to infinity, xt, that is going to be x1, isn't it? Right? So that means x1 is an asymptotically stable critical point. Is it okay?
Yes, sir.
Fine. So what we are going to do, we are going to use this idea. Basically g prime x1 less than 0 or greater than 0, giving you stable and obviously you know that, I mean, if this is greater than 0, this is going to be unstable. Right? This is going to definitely move away from x1. Okay? So we are going to use this concept for plan autonomous system. Okay? So with that note, I'm going to end today's class. So I will see